So last time we were here, I think we talked, where did we stop? I think we stopped at, yeah, we're talking about the boost converter, right? We went to the boost converter, right? So did we finish that, or I'm not sure. Yeah. So I compared them outside, yeah, and let me tell you why I made the mistake about the switch positions, because the way I usually try to explain it, you know, this idea, let's say this is the buck converter, right? In the buck converter, can we have the MOSFET and diode on at the same time? No. What happens is when you turn on the MOSFET, you are reverse biasing this diode, right? When you turn on the MOSFET, you are placing this positive potential here, right? So you're reverse biasing the diode, and current flows to the MOSFET. And when you turn off the MOSFET, because the inductor current is continuous, you have chosen the inductor current to be continuous for at least a switching period, right? That's where the ripple comes from. If the inductor current is not continuous, it means you chose a ripple that is very high, right? Then that means the current will go down to zero, right? If the inductor current is continuous, it's because you've chosen ripple, you've limited the ripple to a certain value, right? That means in the switching period, it will never go down to zero. It will be limited to a certain amount of ripple only, right? So because inductor current is continuous, switch is open, then current will flow through the diode, correct? So both of them will never be on at the same time, right? So the way I like to demonstrate this, or draw an equivalent circuit for it, is something like this. Okay, and what does this represent? It represents like a switch that you're flipping, either connecting to the top or connecting to the bottom. So you're either connecting the MOSFET or connecting the diode, connecting the MOSFET or connecting the diode, right? Do you agree that this can represent that? This is a switch that moves up and down, right? And if you represent it this way, then it doesn't matter what you do with the switches, right? Because here I've removed the switches, right? And that's why I don't know, when I drew both circuits, I drew them exactly the same, and because I'm used to drawing this, right? So if I draw it this way, then here, if I put the source, and here I put the load, you can put a capacitor here, or you could put a capacitor here, it does not really matter, right? This is a stiff source, stiff voltage source, so fine, you can put a capacitor, and you will need it later. We will look at why we need it, yeah. Here we will need it to filter the output voltage ripple. But this block is the same here, and this block is the same here, correct? Now if I put my source here and load here, and I can put a capacitor here, and I can put a capacitor here as well, then this is my buck, and this is my boost, right? Then comes the point where you select the switches that you put in there. And that's where I went wrong. I think I put the switches from the beginning. So how do you select switches now for this? If you go back to our very first chapter when we were actually selecting switches, we have to, now we have to do this. We have to sort of draw this in a little bit of different fashion, right? I draw this way, where I put my capacitor, and then I can put, here's an empty space for this stop switch, empty space for this bottom switch, and then my inductor, capacitor, and load. Current is flowing from my source to my load, right? So I'm either going to put a diode or a MOSFET or a control device, right? So I have the option of putting a diode or a MOSFET, right? Current is flowing in this direction. So can I put this MOSFET down here? The current is coming in this direction, right? It's flowing to the circuit this way or from the source this way. So can I put the MOSFET here? I cannot, because this MOSFET flows current in this direction only, right? So this MOSFET will have to go up here. And then the diode. Can I put this diode upside down? I can't. The only way I can put this diode is actually this way, right? So in a circuit where the voltage polarity on these two terminals is like this, and the current polarity is like that, there is a specific configuration of switches that you can choose. And this is what it looks like. And if you go back to, there's one slide I skipped at the very, very beginning, because I mean, it was not something we can cover at the very beginning, but I can talk to you about it now. You will understand it now. This slide. Okay? What does this slide say? This slide says that if the voltage polarity across these two switches is in this fashion, and current is flowing out of this node, then this is the switch configuration that you choose. Okay? Let's go back to let's look at the boost converter and see if we can do the same thing with the switch selection for the boost converter. The boost converter we have here, how does it look like? So current is flowing which direction? From the source, this way, and then can go this way. Remember, when this switch is closed, I'm charging the inductor. When this switch is open and connected to the top, I am taking this inductor stored energy and the source and dumping that energy onto the capacitor, right? That's what we're doing in the step-up. So this is the direction of current flow, and then this is the polarity of voltage. Correct? So now, this is my polarity of voltage across this configuration, and current is coming into this node. So let's go and see what switches we select. So current is coming into the node, and the polarity of voltage is like this across the two switch combination. So you put a diode here and a switch here. Okay? And then if you flip the voltage polarity and the current is coming out, you may have a configuration where you want to do that. You will choose this configuration. You may choose this configuration. How about in an inverter where you have current? So this is the voltage polarity. Here, voltage polarity is, this is VT. This is V, meaning the voltage polarity across these two. I call these two terminals the throws. Terminals, VT, terminal voltage here is positive. Here, terminal voltage is flipped, right? So this is the positive voltage across the terminals, negative voltage across the terminals. So these two circuits for negative voltage across the terminals. And this is for current, positive. Positive meaning coming out of the node. Coming out of the node, right? These two are coming out of the node, and these two are coming into the node, right? So that's what this meant. How about if in an inverter, in chapter 8, we will cover inverters. So we will have DC to AC inverters where we will have a certain voltage polarity at the input of my converter, right? But I want the output to be both, to have current coming out in the positive direction as well as in the negative. I'm creating AC current, right? In that case. So I have to combine these two, right? How would you combine these two? You can think of ways to combine them. If you combine them, so if you think of combining them in series, you'll put this switch in series with this switch. Will it work? Take this switch and put it in series with this switch. Then current is flowing down here, and current is trying to flow up here. It will block any current coming from this switch. Correct? So this combination would definitely not work. So the only combination is series or parallel. So how about you put these two devices in parallel? If you put the top two devices in parallel, the bottom two devices in parallel, then you've solved your problem. Current can come down through this switch in a controlled fashion, and can come up uncontrolled through the diode. But if I put a second leg that also has a switch at the top that is going to control, or at the bottom that's going to control the current that's coming to the top diode here, then I'm able to control current in both directions. Right? So So this is chapter 8 material, but it's actually, I think it's drawn later here. I talk about combining them later here. So this configuration, here I've combined, I want current that's both positive and negative, and voltage that's fixed polarity, terminal voltage is fixed. And that's an inverter application. So you combine the switches in parallel in this fashion. This way I can control current coming down, current coming up is uncontrolled. But if I add another leg to an inverter, for example, that will allow current to be controlled on the way up through this diode, then I should be able to control current in both directions. Yeah, you missed a lot.
No, I just have a question. Why would you have the same thing on the bottom? It's an AC current, right?
Yeah.
But why would the same thing be on the bottom? It wouldn't allow the negative current to flow through.
What do you mean the same thing would be on the bottom? So typically you have your load here between two of these.
Yeah.
So current will typically flow through here, and then through the load, and typically and then through another one of these combinations here. So I can control current on the way down, right? Or if I have another leg like this, I can control current in this direction. I can control this switch and this switch that I control current in the opposite direction, right? So again, we'll talk about this in chapter 8. The objective here was how do you select switches based on this chart that I had here that we did not go over in chapter 1 because it was too early to discuss that, but now it makes a lot of sense, I hope. Right? So now it's any power converter that you want to build, by knowing, okay, how does the voltage look? What does the direction of current look like? You can now substitute it with proper switches, yeah. Okay. So yeah, this was the reason I made the mistake and then corrected it last time. It's because I typically start by representing it this way and removing this abstract representation of the two switches and replacing them with switches based on current and voltage polarities. Okay, so is this clear? Again, this is additional for you. This is for additional understanding. But at the end of the day, you have the buck circuit is there, boost circuit is there, buck boost circuit is there. But this is nice to build additional understanding, because this you can use to build different converters now. You can take this and build a multi-level inverter. You can take this and build any other kind of inverter. Any power electronic device. Remember we said, what does this represent? This represents that you have one path for current and another alternative path for current when inductive current is there, right? And this is power electronics, right? We said at the very beginning, in power electronics we don't have the single pole, single throw issue that we have in power systems. We don't have a switch that you open up and then have current existing in there causing a big arc to flow, right? Because in this case, a power system circuit breaker does not have an alternative path for current to flow, right? You have to interrupt the circuit. That's what the circuit breaker is doing. It's interrupting the circuit, right? So a big arc will develop. We cannot do that in power electronics, so we always have an alternative path for the current to flow. This alternative path can be a diode. This alternative path can be a diode switch combination, right? So if you go back, I think here, here I combined these two, right? But how about if you want a converter that operates in all four? You can do that. So I don't know if I have that combination for you or not. Maybe not. I'll show it to you next. I'll add it or show it to you next time. But it's possible to do that as well. So it's a bidirectional switch. So people are trying. Actually, this is what people are trying to achieve with power electronics devices. They are trying to develop, bidirectional switches that can control current in both directions. MOSFET can only control current in one direction, right? And that's why we'd add, a second leg. Here, I wanted to control current in both directions. Here, positive current and negative current. So I had to combine these two circuits together, right? But if I want to control current in all four directions and block voltage in all four directions, then I should be able to combine all four of these somehow.
The switches you used are IGBTs?
It doesn't matter.
It includes the diode as well, right? No, the other one.
Which one?
The modified circuit that
This one that combines the positive and negative? Yeah, I basically took this switch and put it in parallel with this diode. Took this diode and put it in parallel with this switch. Here.
Is that what an IGBT was? Or?
I mean, IGBT actually, you typically buy an IGBT as a BJT or IGBT, but with a diode, yeah. You typically buy it that way. But you can buy it without the diode. Yeah, you can buy it without the diode, yeah. IGBTs. Here, IGBT without antiparallel diode, with antiparallel diode. You can buy this or that.
You say they're trying to make switches that control the current in both directions.
Yeah. I think Xis maybe has.
It just doesn't seem very practical.
Why?
I
That's
mean,
the best
because
thing. That's the best thing you want.
Yeah, it seems like that would be the ideal thing, but like I don't understand how they would potentially do that.
So one way to do that is to put, for example, I think.
Like yeah, it's not right. The most practical thing to do is that, but I don't see how it's actually feasible.
Xis.
So you want an example of application?
Yeah, I want to see like.
No, applications there are many. I mean, you would love to be able to control current in both directions. We just saw that, right?
The application's there. It's just the practicality of being able to make it.
Here. Do they have a picture of what they have? Here. 320 volt bidirectional switch capability for high voltage interface applications. So people are working on that. So I don't know if they have a. I think Xis is the only one that has something. I think. But I don't know if they have a data sheet that we can find quickly. Yeah, I mean, you need to search a bit. I mean, I cannot find it.
They have a picture of it up,
No, it's. I mean, you can do it. I mean, if you think of it. For example, you can do it this way. And then you can do this. Reverse one. And then you can do. Yeah. So if you do this, you will allow current to flow. You can control current flowing in this direction using this MOSFET, right? And current will never flow back through this MOSFET because of this diode. And you can control current flowing in the opposite direction because of this MOSFET, and current will never flow back into this MOSFET, into this leg here because of this diode, and here it's controlled. And current here in this path is controlled because of this MOSFET. Current in this path is controlled. So the way to do it today would be 4 devices, right? So how does Xis do it on the semiconductor scale? I don't know, honestly. But you can do it. So, and that's, if you read some power electronics literature, people are using this in what's called a matrix converter. So a matrix converter is one kind of AC to AC converter. And again, this is more of an advanced power electronics topic. It's a kind of AC to AC converter. No, I don't even know how to draw it. Honestly, it's.
You say it's more advanced, but this is more intriguing.
And this is what an ideal switch looks like. Like this is what an ideal when you draw this ideal switch. Like if you actually Google search matrix converter, they will actually always draw it using these ideal switches, because the switch in the matrix converter is required to block current in both directions. You know, our simple switch that we just came up with here can control current in this direction, right? I can only the MOSFET when it turns on can current flow in this direction. In the reverse direction, I have no control, right? So that's why this switch combination cannot do it. The only way to do an ideal switch is something like this. But of course, you do this, and then you get the power conduction losses here, conduction losses here, or conduction losses here and conduction all the time. You multiply the conduction losses by 2. So how do you do it on the semiconductor? Honestly, I don't know how they. I know Xis has something, and I think they're the only company that has something, but I'm not sure. I don't know the design. How do they design it, honestly? But it's like the holy grail of power electronic switches, right? That's the holy grail of power electronic switches.
Senior design.
Fine, if you can come up with the holy grail of power electronics, that's great. I'll work for you later. So it's, anyway, so now I hope the idea of this abstract representation of our switching element, I hope it makes sense, right? This abstract representation and how, okay, based on this abstract representation, I can build a buck converter. I can build a boost converter, right? I look at the voltage polarity, I look at the current polarity, and I go to my sheet here and select the proper switches that can be used in this application. Is it clear how we go to that? Okay. Okay. So now back to the equations. So again, I think we went through the equation in the case where the switch is closed, and did we go? I'm not sure if we did or not, but anyway, for the boost converter, again, the circuit is there. We derived the circuit. We understand hopefully what all the components are doing. I think we spent a lot of time on that last time, and we'll do the same thing. We calculate VL, and when the switch is closed, VL is equal to the source voltage, which is equal to LdI by dt. Di is your ripple current, and the dt, or the time period, is the time for this when the switch is closed, which is capital DT, and you solve for delta I when the switch is closed. And you do the same thing and solve for delta I when the switch is open. And then we know that the current waveform is periodic, so delta I will go up and delta I will go down. The sum of delta I plus delta I when the switch is closed, sum of delta I when the switch is open is 0. The current will not change. There will be no delta I, right, after the full period. And then they use that to find the voltage transfer function. And then we found the voltage transfer function last time in a different way, graphically, right? We drew up the circuit and we drew the waveforms, and we were able to find the voltage transfer function without any of these equations. I think that's where we stopped last time. And then again, we would have to go back. So voltage, I mean, to size up the switch and the diode, we look at the peak voltage and average current. So peak voltage on this circuit, hopefully should be clear. The boost converter circuit. Right. When this is V output, and this is V input, right? When the switch is open, what is the voltage across the switch? Oops. When the switch is open, what's the voltage across the switch? This is plus, minus, V output. Diode, switch is open, diode is short circuit. No, it's V out.
Yeah.
Right? In the buck converter, it was V in.
Why
Right?
are you drawing in reverse now?
Why?
You put the V in on the opposite side than you usually do.
Yes, but it's okay. but I have the right symbol for it, yeah.
Yeah.
Right? So typically, yeah, I draw the buck converter, yeah, I put V in here, and I put my switch here, and diode here, inductor, and resistor. Right? So in the buck converter, when the switch is open, diode is closed, the voltage across it is V in, right? But for the boost converter, when the switch is open, diode is closed, the voltage across it is V out, okay? And it's the same for the diode. If the MOSFET is on and the diode is open, again, it's the same loop, right? So voltage across the diode is also, what's the voltage across the diode when the diode is off and the switch is on? Yeah, V out. Okay, so the switch voltage rating for the boost converter is V out. For the buck converter, it's V in. Okay. Switch current rating, you have to find the average value of current. So how would you find the average value of current? You would have to draw the current waveforms. For example, in this case, the average value of current will be what? You have inductor current, it will have some average value. Average value of inductor current is being what? Divided between the diode and the switch, correct? Average value of inductor current is equal to average value of source current, right? This is source current. So average value of source current is equal to average value of inductor current, right? They're the same. This average value of inductor current is being divided between the switch, the diode here, diode, and the switch here. How do you divide them up? Based on duty cycle, right? So part of that average current is flowing in the MOSFET, and the rest is flowing in the diode. Which part is flowing in the MOSFET? Duty ratio multiplied by the average value will flow in the MOSFET, right? This is a percentage, right? It's a percentage. So if the duty ratio is 50%, then 50% of the average current is flowing in the diode, in the MOSFET, and 50% is flowing in the diode, right? So if I tell you, for example, you're developing a boost converter for a load, for a 5-watt load, and your output voltage is, I don't know, 10 volts, then what is your output current? P equals V times I, right? This is DC, right? And this is 5, this is 10, what is I? Half an amp, so this is half an amp flowing here. And if I tell you the system is lossless, right? Your power converter is lossless. What does that mean? It means that whatever power is coming in is coming out, right? So that means your supply here is 5 watts as well, producing 5 watts. And you typically have your supply voltage. This is a step-up converter from, let's say, 5 volts, 5 watts to 10 volts, 5 watts, right? It's a 100% efficient system here. So if you have 5 watts and 5 volts here, can you calculate the average supply current? Yes. If you have your average supply current, you can calculate. This is the same as the average inductor current, right? So average inductor current, and now you know your voltage transformation ratio. From the voltage transformation ratio, you can calculate duty cycle, right? Because we said for the boost converter, V output is V input over 1 minus D. You have V output and you have V input. So you can calculate the corresponding duty cycle you need to operate your switches at. Knowledge of the duty cycle, you should be able to calculate now the average current flowing in the switch, or the average flowing current flowing in the diode. Do we see how to? So we sized up the switches fully, right? We know the peak voltage across them, and we know the average current flowing through them. Any questions on this? We're good? Okay. So switches done. Now what we have left? Inductor and capacitor. Inductor and capacitor, same as before. We have to look at the waveform, and from the waveform we can calculate the size of the inductor. Or we go through the equations like they're doing here, and then they will also introduce the waveform technique that I like to use. Yeah. So this is they've calculated voltage transfer ratio. They what do they do next? They want to calculate this I maximum and I minimum flowing through the inductor, right? So that's the objective of what they want to do. Inductor current, we said, is what? Has an average value equal to the average value of, in this case, the load current. Okay, let's see. I think they equated, yeah, they equated input and output powers, meaning they assume the system is lossless. So this is input voltage times inductor current, average inductor current, which is equal to average source current, we said, right? Equal to V output squared over R. So they equated the input and output powers, right? And then replaced V output with the voltage transfer equation that we just came up with. And then they were able to solve for IL. right? They solve for IL in terms of the rest of the variables, and then again you have a relationship. So V output squared over R is also the power, which can be represented as V output times I output. So they found the relationship between IL, I output, V output, and Vs. Right? So IL times Vs is also V output times I output. I mean, it comes from the fact that I equated the powers anyway, right? So the source average value of current multiplied by the source voltage is equal to the output voltage multiplied by the output current, right? I mean, they didn't. So what do they do next? So then they calculate delta. They would like to calculate. So we calculated before delta I when the switch is closed, right? And then what they wanted to do was calculate this I max and I min to be able to calculate the minimum value of inductance for continuous current mode. I max, I min is more important. So I minimum is equal to what? The average value of inductor current, which is equal to the average value of source current, which if we equate powers and assume the system is lost, this is equal to the average value of output current in this case, right? Minus, half of the ripple, right? So it's inductor current has an average value, and this average value, this is my delta I, so this is half delta I, and the bottom one is half delta I. Delta I over 2. Right, so minimum current is equal to the average value minus half the ripple content. The value, the equation for ripple we came up with from up here, right? Either when the switch is closed or when the switch is open, right? So that's what they substituted with here to be able to come up with an equation for I max and I min. After you get an equation for I min, you substitute with I min equals 0, right? Why is that? Because we want to calculate the minimum value of inductance that will allow my converter to operate in continuous conduction mode, right? It's a critical value of inductance, something you want to know, right? So they were able to calculate the minimum value of inductance. Of course, if you want to calculate a specific value based on a specific ripple spec, you'd not need to do that. You would go to the delta I equation, the ripple current equation that we derived before when the switch is closed or when the switch is open, and you can, given V input, given the duty ratio, because you know the voltage transfer equation, and you know your switching frequency, you should be able to calculate the specific value of inductance that you want, right? And this is what we're doing graphically, right? This is actually what we're doing graphically. Capacitor, same thing. I mean, it's a repetition of what we did before. So it's you will have to draw the capacitor current waveform. So let's see what the capacitor current waveform looks like in this case. For the boost converter, let's draw the boost converter. Let me confuse con and draw the voltage source on the other side. Right?
That's when you switch it.
Huh?
That's when you switch it.
I just switched it. I switched it now. I made it more difficult.
My simple mind can't handle it.
Okay, so now we size the inductor up, right? And this is my input, or they call it Vs, and this is my output, right? And this is the capacitor I would like to size up. So how do you size up this capacitor? I would like to, how did we size up capacitors generally? We said that C is equal to delta Q over delta V. This was a spec, typically, and this was the area under the capacitor current, right? So that means we need to find the capacitor current. Where is the capacitor current? Current that is moving here, right? So I need to be able to, where is that coming from? It's coming from this side. So the current in this branch is the diode current. Do we agree? So now, this diode current, is it a pure DC waveform? What does this diode current look like? What does ID look like? Let's do IL. Okay, let's do IL first. Okay, this is a switch that is receiving this gate signal. Okay, when the switch is on, what is the inductor voltage? Actually, let me do VL first. When the switch is on, what is inductor voltage? Oh, when the switch is on, what's inductor voltage? Exactly, so it's Vs. When the switch is off,
Be negative or zero.
uh,
Go backwards.
no, the voltage here, yeah, the voltage right here is when the switch is on, it's zero. So when the switch is on, the voltage here is zero, and when the switch is off, the voltage here is what? The switch is off, the diode is on. So the inductor is seeing what? V out on this side and Vs on this side. So it's seeing a Vs minus V out, right? So on one side it's seeing Vs, and one side it's seeing Vs minus V out. Do we agree? When the switch is on, inductor voltage is Vs. When the switch is off, inductor voltage is Vs minus V out, right? Here it's Vs, here is V out, so it's seeing the difference between them. Okay? So this is the inductor voltage. Do we agree? If this is the inductor voltage, what does the inductor current look like? It's IL is equal to 1 over L integral of VL dt plus some I0. I0, we're operating in steady state, so we'll have some minimum value, I minimum, right? We calculate the I minimum always. So we have some minimum value of current, and then what do? We have a positive, VL is positive voltage, a positive fixed value, so it's a positive ramp. Then it's a negative fixed value, then it's a negative ramp. Positive, negative, positive, negative, right? This is IL. We said IL is what's coming into this node, right? It's splitting between the diode and the switch. When the switch is on, IL is going to go into the switch. When the switch is off, it's going to go into the diode, right? So here a switch was on. So if I want to draw I diode, what will it look like here? 0. And then what is it going to look like here? Like IL. So it's going to look like this negative ramp. Okay? This is the diode current, right? Now, this is what I have here. Now I want capacitor current. Go back to the same logic we were using, right? This diode current, is it a AC current or is it a DC current? Or is it a combination of both?
DC. Combination.
Yeah, DC means flat. DC means flat. This is a combination, AC plus DC current. Here, AC plus DC current coming into this node. This, ideally, is an infinite capacitance. So 1 over omega C, C is infinite. So anytime I have any AC component, where is it going to go through? The capacitance. So how do I draw the capacitor current? I take this waveform, remove the average value. Right? So I take this waveform, remove the average. Average value of this is something, I don't know, something around here. So I shift this waveform down by its average value. And that's what's going to be in the capacitor. That's the capacitor current. Right? And that's what you will see they've drawn here. Right? So this is the diode current that we just drew. Then they shifted it down by the average value. After you shift it down by the average value, then you can calculate now the area. It's easier to calculate this area, of course, than this area. You can calculate either area, it doesn't really matter. Right? But easier to calculate the area of a rectangle versus an area of something like this. Fine? So they just calculated the delta Q here. Given delta Q and given a delta V spec, you should be able to calculate C. Okay? Of course, this is assuming the capacitor is ideal. Now, if they tell you that to include the ESR, then what do? You have to calculate again. The ESR will have the resistance. It's a resistance in series with a capacitor. This resistance will see a voltage drop across it due to this current, right? So it will see a voltage drop across it, the same shape as this, scaled by the value of the resistance, right? So the delta V due to the ESR is equal to delta I, this delta I that you have here, multiplied by the ESR resistance. Okay, so that's how you would include the delta V due to the ESR. Then you take your delta V due to the ideal capacitance, delta V due to the ESR, and they both should be less than your spec. Right? Yes? No, really. Is it clear? Okay, so that's the boost converter. So we said that, yeah, the voltage transfer ratio of the boost converter, we said, is V output, is V input over 1 minus D. That was for the ideal boost converter, right? Forget about this part yet. For the ideal boost converter, what is for a duty ratio of 1 minus 1 is 0, so this is something over 0, which means the output voltage is infinite, correct? And that's why we have this curve up here, right? But we talked about last time the effect of putting considering the effect of inductor resistance. So if we consider the effect of inductor resistance, I'm not going to go through the equations for that. I mean, you can use the equation, you can put in an equation sheet, or you can look at the derivation in the text. But the main idea is, we said that if I now consider the fact that I have a resistance here, RL, this RL is going to see the source current flowing through it. It will have an I squared R component of loss. Anytime my load draws more power, my source has to deliver more power. It's a fixed voltage, so the current will keep increasing. Current keeps increasing, and you are squaring it and multiplying by the resistance and subtracting that from the voltage that you're able to boost with, right? So you're trying to boost, but this resistor is pulling you down by a squared fashion. You try to boost, the resistor is pulling you down by a squared fashion, right? So you end up with a characteristic for the real boost converter looking like this. If you consider only the effect of the inductor resistance. Of course, if you consider all the other losses, they will give you a similar effect here, right? But it may be more pronounced. If you consider the switch losses, for example, if you consider the wire losses, if you consider, it's the ESR of the capacitor, if you consider all the other losses, again, you're going to just move away from the ideal curve and get closer to the, this will go down quicker or something like that, right? So in the textbook, they just consider the RL that we just talked about, the inductor resistance, resistance in series with inductance, and they just drew the curve, the ideal curve, the non-ideal curves in that case. And we see here that again, for a real boost converter, the step-up ratio is not infinite. That's why in your project you cannot use the boost converter, right? You wanted to boost from 12 volts to 180 volts. There was no way to do that with a boost converter. So we had to use a more complicated topology. We will cover that more complicated topology in chapter 8 when we talk about inverters, because it's basically a DC to AC high frequency. That's what he did. You converted from DC to high frequency AC and then rectified that, right? That's what you did in your project. So that DC to AC we will cover in chapter 8, the next chapter. So that's the only way to do it. That's the only other way to do it, because you cannot boost from 12 to 180 volts with a boost converter. That's the reason, yeah. Okay, what else? Of course, efficiency will be the same, right? We were talking about efficiency being, input power equal output power, right? If I consider RL, that's not the case anymore, right? Initially, I was considering inductor being lossless, switch being lossless, diode being lossless, capacitor being lossless. So input power is equal to output power. And the problem that we went through, where we calculated the average values of current, I can tell you, instead of the converter being 100% efficient, converter can be 90% efficient. In that case, fine. You given your load is 5 watts, 5 volts, for example. Then what is your input power? For a 90% efficient converter, the input power will be 5 times 1.1, right? So now you have a different input power. Your input voltage, you will typically have it, let's say 2 volts in this case, because I want to boost to 5, for example. So given your voltage, your input power, you should be able to calculate your input current. It's the same process, but I just added a variation to what we did, which is efficiency of the power converter. So as you would expect, of course, the higher the duty ratio, the higher the boosting ratio, the higher the current. The higher the average current, the current through that lossy resistor, it's multiplied, it's squared, the loss there is squared, meaning you will probably be losing efficiency quicker as you increase the duty ratio. And that's what this curve talks about. That's what this curve is showing. Right? So efficiency is equal to output plus over output plus losses. And the losses here are due to the average source current or average inductor current squared multiplied by that resistor value that we talked about, the inductor resistance. Okay? You're okay. And they just rewrote it here in terms of duty ratios and based on what we the voltage transfer ratio that we had before. This complicated voltage transfer ratio, they just rewrote the efficiency here after simplifying and substituting with the voltage transfer ratio. So you can do it either way. It does not really matter. So as the duty ratio increases, the efficiency of the boost converter decreases, and we said why? Because of the average value of current flowing through that resistor, right? That we put in series with the inductance. Every time you increase the duty ratio, the current there increases. So I squared R increases in a squared fashion. Okay, the last DC converter we'll talk about is the buck boost converter. Exact same thing. I mean, the idea is very similar, but the nice thing is here we can, in the boost converter, the minimum output was equal to what? If you look at here, the minimum output voltage was equal to the input voltage, right? Why? Because if you kept the switch off all the time for the boost converter, if you keep the switch off all the time, the diode on all the time, you're just connecting your input source to your output resistance, right? So your minimum value for a duty ratio of 0 is equal to the input voltage. So your minimum value of output is equal to input voltage. So sometimes you want to be able to bring the voltage up and you want to bring the voltage down. You want to step up and step down at the same time. An example of that is, for example, maximum power point trackers in a photovoltaic application. In a photovoltaic application, you have the voltage output from a PV panel. You would like to extract the maximum amount of voltage that you can from that converter, at the same time feed a fixed load at the output, feed a battery, charge a battery, right? So the input voltage is sometimes, the maximum power point will sometimes occur at a high voltage, sometimes it occurs at a low voltage, right? Compared to the battery voltage on the other side. So sometimes you would like to buck and boost the voltage from a converter, not just buck or boost, right? So we'll go through the same logic. So we'll calculate VL when the switch is open and VL when the switch is closed. Calculate I minimum, calculate L minimum, exactly the same process, yeah. Again, switch is closed, we look at VL. VL is equal to VS, so we calculate a corresponding delta I equation, right? And then we do the same thing when the switch is open. But also one thing to note here. We will always have this, remember this, when I represented these two switches in an abstract fashion as this, single pole that's, going between two nodes. These switches are always complementary, right? Always complementary, and typically, and always will have an inductor in the middle. You change the converter, but you will see the same thing. the switch, one switches, if the switch is here, the diode is going to pick up the current when the switch is open. If the diode is open, the switch needs to pick up the current, right? So they're always going to exist together, and they will have an inductor in the middle. And at the terminals of the combination, there will be stiff voltage sources. Here I have a strong capacitor. Capacitor will not allow voltage to change quickly. A voltage source here, stiff voltage source. Same thing with the boost converter. The two switches with an inductor between them. And then across the two switches, I always have a stiff voltage source. Right? Go to the buck converter. Same thing. The two switches will always have an inductor between them. Across them, there will be a stiff voltage source. Right? Because what you're doing is you're taking that voltage source across the two switches, you're taking that, chopping it up, and putting its average value after the inductor. That's what you're doing in all the circuits. Right? Regardless of current flow. So regardless of current flow, across the two switches is a voltage. At the other side, between the inductor and the ground terminal, you will have the average value of that voltage across the two switches, depending on your duty ratio. Always. Just the current flows in different directions. So switch open, switch closed, we calculate DI. So here switch is closed, we calculated DI, VL is equal to VS. Switch is open. In this case, now switch is open, diode is closed, VL is equal to the output voltage. Right? VL is equal to the output voltage. And then you calculate the same thing, calculate delta I. And then delta I up, delta I down. There's no change in delta I, so the sum of the two delta I's is 0. Right? There's no change in current, so you do the same thing, and from there you will find the voltage transfer ratio. One thing to note is the negative sign here. Right? So here the output voltage polarity is flipped. In the buck boost converters, the output voltage polarity. So if you put a battery, that the output will be flipped. That's what this is saying here. Yeah. Okay. So the process is the same, right? We just the VL, add the two delta I's, and calculate V output. Then what do? We have to calculate value of L and value of C. Value of L, before we do that, calculate the critical value of inductance. So we find I minimum, right? I minimum will equal to the average inductor current minus half the ripple. Same process. It's the same process repeated. Yeah. I don't show the. Oh. For some reason I don't have the slides for the L, but I mean it's in your textbook, or we can draw the equation. We'll draw the waveforms anyway. Capacitor value, same thing. They do the same trick here. But now let's draw the waveform to make sure that the capacitor waveform is clear. Okay. So let's go back here. And see what's happening. So we have our source here. We have our switch here, and our diode here, inductor here, capacitor here. This is VS, V output, but V output is negative actually, so V output is equal to, what did we say? V output is equal to minus VS D over 1 minus D. Oops. Where's the, oops. Minus VS D over 1 minus D. Minus VS D over 1 minus D. So what is the range of V output? For D equals 0, what is V output?
Or 0.
Yeah, it's minus VS times 0 over 1. So it's 0, right? So minimum value of output voltage is 0 now, right? And for D equals 1, V output equals minus Vs, 1 over 1 minus 1. So it's minus infinity. So this converter can give you from 0 to infinity, well, theoretically speaking, again, right? Like the boost converter, right? It will, as soon as I put a real value of, something real here, like the resistance of the inductor, for example, this thing will, again, inductor current will flow through this, through the resistor. The power loss will be squared. The energy that I'm able to transfer between the inductor and capacitor to the output will be lost by its squared, but in proportion to its squared value, for example. And I will not be able to boost enough. Yeah. So now, initially, let's do without. So I would like to be able to size my inductors and capacitors. So we go through the same process, right? So when the switch is closed, we said the voltage across the inductor is Vs. So I'll draw VL here. So Vs. And when the switch is open, so this switch is open, a diode is short circuit, the voltage across the inductor is minus V output, right? We agree? It's a negative number, so it's minus V output. So waveforms are very similar, right? IL, what does IL look like? IL looks like, again, it's the integral of fixed value, so it's a positive ramp, right? When is this? So this is occurring when switch is on, right? And then switch is off here. So I would like to be able to look at diode current. So to calculate the inductor size, so L, to calculate the inductor size, I need to calculate delta lambda over my delta I spec. Delta lambda is the area under the inductor voltage curve, right? So how do you get the area under the inductor voltage curve? You know your duty ratio. From where? From here, right? You're going to be given input and output voltage. I mean, this is a spec. Your load wants a certain output voltage. Your input voltage x, y, z. So given input and output voltage, you should be able to calculate your duty ratio. So that's done. So given your duty ratio, and you know how this waveform looks like, it's a rectangular waveform. So this is dt. This time period is dt. So this is, you know this, and you know the height here is Vs. So you can calculate this area, volt seconds. You can calculate this area in volt seconds. Take that and divide it by your current spec, ripple current spec, and you will calculate your value of inductance. So that's the value of inductance. So value of capacitance. Value of capacitance, you have to look at this node here. You have to see the capacitor current is now this here. And remember, this is actually negative. The voltage is negative, so the current is actually going. So the resistor current and the capacitor current are equal to the diode current. Do we agree? So to calculate the diode current, I need to look at the inductor current. Because basically the inductor current is where? Inductor current is here. And inductor current is a combination of the source current and the diode current. Right? When the switch is on, the inductor current is equal to the source current. When the switch is off, the inductor current is equal to the diode current. Same thing we did before, right? So now our objective is to find the current in the diode, which is the inductor current when the switch is off. So this is the inductor switch is off. So this is my inductor current when the switch is off. It's equal to my diode current. Same thing now. This diode current, is it a DC component? Is it a DC current? No, it's a DC and an AC component. The AC component will flow through the capacitor. So I take this, remove its average value. That's the current that's going to flow through the capacitor. You take that, draw that current flowing through the capacitor, and then to size up the capacitor, you take the area under the current curve, and so which is this or this, does not really matter, right? You take the easy one, right? And then that's your delta Q. Given a delta V spec, you should be able to calculate C. Okay, so it's the same as exact same as what we did in the other one, in the boost converter. And here they have the equation for it. They do the same. So the waveform is what we derived, and they take the easy rectangle that we decide to take as well. Given delta Q, knowing your delta V, you should be able to calculate C. So that wraps up the three main converters. We will wrap up the chapter next time. So try to go through and make sure we don't have any. I mean, these are the main topics, the main three converters. We will wrap up. We add some spicy stuff to the converters so that we understand a little bit more interesting things. But nothing. I mean, I hope you see that the calculation of the capacitor and inductor value in all the converters is very similar. It's very similar if you understand the waveform. So I would draw the three converters. Make sure you can draw the waveforms in every branch. If you feel comfortable doing that, then you know what you're talking about. So that's it for today.
Does anybody have class at 4 o'clock or later?